Okay, so in this video, we're using the Polarfire SoC Icicle development kit from Microchip, and we're going to have the MSS, the microprocessor subsystem, will have one of its RISC-V processors access memory that's located in the FPGA fabric using the AXI bus, the high-speed AXI bus. So first thing, let's open up Libero or Libro. Icicle likes version 2023.1. We open up the project file. I can click on this because it's my latest project file. But if I hadn't opened it, I would left click on project, left click on open project, navigate to where I have my project. I believe it's an Icicle. Ooh. Maybe it's an ice. Okay. Here's the Icicle kit reference design that is downloaded from GitHub. And this MPFS Icicle, go down into that. And here's the MPFS Icicle PR project file, PRJX. Double click. And now it's loading the project. And we're going into Libro just to show where the memory is and at what memory locations. But we'll do most of the work in SoftConsole. Okay. Dismiss, left click. Okay. So right now this came up, but if it didn't, you'd go to the Design Hierarchy tab and double click on MPFS Icicle Kit Base Design. Double click, double left click. And in this, see some schematic. This is the schematic of the FPGA fabric. And then some. I guess it's the entire FPGA. Because you could scroll in and out on this and out by pressing the control key and middle mouse wheel. You can see this is the MSS wrapper. That's where the RISC-V processors are. There's a few other little blocks. This FIC0 peripherals is where we're going to end up going. That's on the AXI bus, and you can see that it's on the AXI bus. So it's got this AXI right here. Let's click on that. You can see that's coming from the MSS wrapper. There's also the FIC 3, which is a slower speed but smaller and simpler interface to the MSS. This is where we did work on Blinky and the SPI interface to an ADC, and we did those in previous projects in this playlist. And then we got FIC1, which is another. So zoom in, you can see that it is also the AXI bus. And you can see it goes to the MSS. And we just drop down into this one. This one primarily looks like it's got a PCI Express interface. but it doesn't have any memory in it. So let's pick 1, FIC 1, scroll back up, and double click on FIC 0. And in this one here, you can see 4 blocks, of which there's this FIC initiator, which is really like a bus splitter. It takes this input here from the MSS, so it's the AXI bus from the MSS, goes into this bus splitter. Part of it goes to this DMA controller initiator path, and part of it goes to the this MSS LSRAM. And LSRAM is one of the 2 types of memories that the fabric has in Polarfire. If we double click on this, you can see that component is this. You can select it, Control C, maybe go to the browser, Control V, enter, and you can find that Microchip has some documentation on this block if you wanted to read about it. Let's get that out of the way. But here you can see that the depth is 2K 2048. It's got a few other parameters, and the data width is 64 bits, so it's a 64-bit wide bus. It's a 2048, so 2K, so it's 2K by 64. So if you wanted that by bytes, multiply this by 8, and so we've got around 1600, 16K uh, of memory. All right, so that's what this memory is. So that's the size of it, 2K by 64. You can do things such as memory initialization. So we can load some contents. If you click this initialize button, and you can click on this, you can then search for a file, like an Intel hex formatted file, and load that in, and that would be kind of like serving as a PROM. I gotta figure out how to do that, so that'll be another video. Let's close that, cancel out of that, and then so this is this block. Let's go to the initiator, and we want to know what address range this guy is sitting at. So when we double clicked on the initiator, it's thinking about it, and here it comes out where it's got one controller, which is the MSS processor. So even though there's 5 RISC-V processors in the MSS, they all get funneled down into like a single. All 5 of them can access this AXI bus, and so it gets funneled down into one M interface. And then we've got slaves. I mean, we got the number of outputs or peripherals connected to it, and we have 2, which is we saw the DMA. We saw the DMA up at the top part, and the MSS at the lower part, the LSRAM at the lower part. So we got 2 of those outputs, and now you can see how the master is configured, which it's a 64-bit bus. There's got a FIFO depth of 16, and that kind of is how big of a burst can it hold, and that affects how fast its transfers can go. And then we have the configuration for the peripherals, and we've got 2 of them, again 0 and 1. And 0, which is the DMA, has a data width of 32. And the second one, which is our memory, has a data width of 64 bits. And here's the important thing that we're looking for right here, is that the starting address is at 6 and all zeros. So what we're going to want to do is write and read to that to this location and the subsequent locations, and see if we can access that. So that's all we're going to do here in Libero. So we're going to cancel that, minimize him, and we're going to go over and we're going to start Soft Console. Click on this, and Soft Console is going to come up. And this is our workspace. So we're going to launch it. And I just went through this, and video is really just for me to remember what I did so that I can repeat this sometime in the future. And so here we've got the E51 processor that if it opens up, you can see like in this project, we got a source directory, applications, the heart 0, which is the E51 processor. The other hearts are these U55, which are U54, which are slightly higher performance, but the E51 is easier for me to use. And so what I did here is right here, XV, this guy. So I created a pointer to address 6 and all zeros. And I called it a uint and a pointer. And I'll also call it over here a uint and a pointer. And that is the base address of the block of memory that we saw, the 2K by 64 memory. So now what we're going to do is we want to write to quite a few addresses after this. So, what I did like just before this, and I don't want to forget how to do it, is I guess we could try it again. You can probably read it just fine, right? I don't need to type it. So this first part fills like 100 locations. Let's fill. So we now know that there's like it's 2K deep by 32, and we're doing axes of we call this 32 bits wide. I wonder why we didn't call it 64 bits wide. Maybe we'll give that a try in the next variation of this. But we have let's go with 2048. I think there's still some space left over, right? Because there's so these are 32-bit addresses. I guess it's interesting to have a 32-bit address access that 64 address space. We'll see how that works, and which I know it does work because I've done this one just now, just before this video. And so here I'm filling it up with the value of the loop counter. So I'm putting into each one of these memory locations a value from 0 to 2048. And I created this little fail count variable. And I also created a val, which is going to get the return read value. And then again, I loop through it 2K times. And we basically here we're reading the memory location like out there at that 6 and all zeros, and then 6 all zeros and all offset. So we're reading those. That goes into the value, and we compare value with II, which is what we wrote into it, and and if it doesn't match, then we increment this loop counter, and then this is from like the reference design from one of the bare metal examples uh, on using the UART. And so it's just a while loop that continues on whenever there's data that's got received from the UART, which will be connected up to PuTTY on my laptop. So whenever PuTTY sends over like a character, it's going to fall into this if statement. And then what I wrote here is so I got an sprint where I fill this temporary string with LSRAM fail count equals %d ls fail count. And so this here is if nothing failed, then it should return 0. If something failed, it'll tell how many times we failed. And then this here squirts that string out of the UART to putty, and it should show up on the putty screen. So that's pretty much what we're doing. Let's give this a shot, and let's compile with a left click on the hammer. This doesn't take too long. Definitely takes much less time than resynthesizing the FPGA. And so this is my previous putty session. Kind of pretend it's not there. All right, but we do have putty connected up. And now, so we've just finished compiling, 0 errors, 0 warnings. Took 21 seconds. And now we're going to left click on the run button right here. And this is starting up. Scrawls a lot of stuff in red, but that's just informational. And when it's done loading and everything, it's going to get to here. And it's going to halt because we're in debug mode. And then there's this resume F8 button. So you can press F8 or you can click on this little green resume button. And so we'll left click right now. So now it should start running. And so now we're going to open up putty. And something's going to pop out down here. Probably another one of these. Press 1 or press 2. All right, so now what it's waiting for is us to hit a character. And when we hit a character, it should tell us results of the memory test, which ran before this polling loop that we're in right now. So let's hit a character. I'm going to press 4, but any character should work. And we'll failed 1,024 times. Well, I didn't fully expect that. When I did it earlier, 100 worked. What's going on here? So, scratch, scratchity, scratch. Let's take a look, see, and let's see if we can figure out why. So right now it's it's giving this MSS UART file. I don't really want to look at that, so I'm going to just left click on the X, get rid of him. It's going to stop, terminate here, the red square box, left click. All right, now we're going to go back to here. Let's cut it down to just 1K locations. Interesting. Okay, Control S, save it. Click on the hammer. Did say 2K by 64. We were only reading 2K by 32. Not understand. We'll figure it out eventually. All right, so it just ran to here. Left click on the run green button. It up here. Wait for the resume button to change color. Okay. Left click on resume. And open up putty. Wait for something to happen. Okay, it says printed out its prompt. Let's hit a letter. Look at that. Fail count of 0. So I think what the issue is if we go back to the Libero, we go back to him. So this guy here is configured so it's 2K by 64, which is really 16K bytes. Cancel. Go back to the initiator. Double click on him. Okay. And if we go to these peripherals. So I got this address here. 3 locations. That's 12 bits. So that's 2 to the 12th. I believe this is a byte address. So that 12 bits really goes up to 4K bytes, which is divided by 4 is 1K 32-bit words. So I believe what they really wanted, that's 1K. So they really wanted something like that would give, let's see, that's 4K. That's 8K. That's 16K bytes of address space. So I believe that is what they really wanted here. Um, so yeah. Um, so I guess bottom line is we are successfully able to access like the 1K address space. Looks like there's a little inconsistency. You could call it a bug, in that they can't access the full 16K bytes of memory because of this being 0 instead of 3. Um, so I'm going to call this video a success. Um, I'm going to also build this in Libero. That takes like 20-30 minutes. And then I'm going to try it again and see if I can get to the full address range. So I'm going to shut down. And then when I eventually get around to running this test, I will might splice another video to the tail end of this video, just showing that this does work now. So let's click OK. Okay, might as well see how we do this, right? So this is this initiator here. Um, Something was funny there. Let's just look at what we just did. Something was misbehaving. So it does that might change. Okay. Something's not happy. Or the debugger slowing things down, causing a problem. Shut down this completely. Now we got a can. Yeah, so I think that debugger was somehow interfering. So we've got this what do they call it? Generate component. Whenever you make changes, I don't know, maybe you can go all the way to the top, but I tend to go one step at a time. Generate component. I go up to this guy, click on generate component. Um, let's build a hierarchy. for all, I think, left clicks on the generate component and the build hierarchy. It might take around a minute. So currently we're in this design hierarchy tab, which shows us this, like the design hierarchy. When we do the synthesis, we're going to switch over to the design flow here. Things have changed, so that's why we have all these exclamation marks. We'll go down and we'll double click on generate bitstream. Just going to rerun all of these steps, and then we'll be ready to program it whenever we get around to doing that. So here we go. Double click on that. We'll shut this video down. But all in all, I'd say so far successful. Okay, we're back. We've just regenerated a bit stream with the fix to increase the address space going to the LSRAM block RAM. See, everything's checked off. Bit streams generated. So then you just double click on run program action. And that's running for now. So while that's going, let's start getting a SoftConsole running again. Let's click on launch. So earlier we had this at 2048 instead of 1K. So let's bring it back to, so let's bring it to 4096. Yeah, because there should be 4096. There was 2K 64-bit words, which means there's 4K 32-bit words. We're reading 32-bit words and writing 32-bit words. So let's, that should work. That should be the full address range. Let's do a Control S. Let's left click the hammer so it'll build. Okay, build was successful. Let's minimize this for a moment. Well, that's okay. So he just finished. Flash Pro stopped blinking, and my blinky lights are working. So the FPGA is booted. So now we can go back to this guy, SoftConsole. And now we just compiled. So left click on the run button. Okay. And it's booted and it's waiting for resume because we're in debug mode. So left click on the resume or press F8. So that's going. Let's open up Buddy. Oh, we have a lot of interesting stuff going on here. Ah, okay. So now, let's see how our fail count does when we hit a character. I'll press 4. Hey, look at that. Fail count is 0. So we read all 4K, 4,000 locations of 32-bit words, which is the full 16K bytes of memory. And the test passed. That's great news. So I think we're done here.